Okay, this is Chapter 2 Notes. The first part of Chapter 2 Notes covers a bunch of stuff about history. So let's talk about Dalton's atomic theory. Dalton's theory had 4 postulates that explained atoms. The first one, all matter is composed of indivisible atoms. We have underlined the word indivisible because we know that this is no longer true, but at the time that's what Dalton thought. He says also that an atom retains its identity during chemical reactions. Secondly, an element is a type of matter that is composed of only one type of atom. Third, a compound is a type of matter composed of atoms of 2 or more elements chemically combined in fixed proportions. Now, this eventually led to the law of multiple proportions. Dalton took this in combination with Proust's law of definite proportions and came up with the law of multiple proportions, which I will go over soon. Fourth one said that a chemical reaction is nothing more than the rearranging of atoms that are already present to give new substances, and that you cannot create or destroy matter, that it's always going to be conserved, which we already talked about in Chapter 1. Now, the law of definite proportions states that a pure compound, no matter where you get it from, always contains definite or constant proportions of the elements by mass. So for example, water. No matter where you get the sample of water from, the mass of hydrogen in water is 2.0, the mass of oxygen is 16.0. And no matter what, when you reduce that, you will always get the ratio of 1 to 8, or 8 to 1, no matter where you get the water from. That's what makes it water. The law of multiple proportions is a little more complicated. When you take 2 elements and you can form more than one compound, so for example, nitrogen and oxygen can form these 4 compounds, N2O, NO, NO2, NO4, okay? If you compare the mass of oxygen in one compound to the mass of oxygen in another compound, you will always get a whole number ratio. So let me show you this with the first 2, N2O and NO, okay? If you only had a gram of nitrogen, okay? Now, when you look at N2O, you know that that's 28 grams of nitrogen because there's 2 N's, okay? So in N2O, it's 28 over, let's say, oxygen. There's only 1 oxygen, so that's 16. Now, if I wanted to have 1 gram of nitrogen and solve for how much oxygen there is, I would get 0.571 grams. I can do the same thing for the other compound and I get 1.14. When you compare 1.14 to 0.571, you get 2. And if you notice, it's a 2 to 1 ratio, or a 4 to 1 ratio, or an 8 to 1 ratio. And no matter what, when you compare the amount of oxygen in 2 different compounds, both formed with nitrogen, you always get whole number ratios. And this kind of makes sense. You can't have part of an atom. You have to have an oxygen or no oxygen, or 2 oxygens or 3 oxygens. You can't have 2.5. Now, you know, I hope, that Dalton was wrong. Atoms are divisible. There are 3 subatomic particles that we know about today: protons, neutrons, and electrons. And I put these 2 pictures on here for a reason. This was Bohr's atomic model. And while Bohr's atomic model is very helpful in describing some of the properties of the atom that we know about, it's not correct today. When you picture the atom, I hope this is not what you picture. Electrons do not travel in orbits in a certain specified path around the nucleus. Today, this is the quantum mechanical model. This is the model that we use today, and it is much messier. The nucleus is in the middle, and the electrons are floating around in this cloud outside the nucleus, and they are all over. They do not stop moving. They are constantly moving, and most of them are close to the nucleus, but there are some that are outside as well. Okay, that's the model of the atom that we use today. So who discovered these particles? The proton was discovered by Eugene Goldstein. I don't expect you to know how or when. The neutron was discovered by James Chadwick. I also do not expect you to know when or where or how or anything like that for him. I will tell you, though, that many students remember that it was Chadwick because a nickname for James is Jimmy. And I know you all love that childhood show, Jimmy Neutron, so you can remember it that way. The last two I do expect you to know more about. The electron was discovered by J.J. Thomson, and the nucleus was discovered by Ernest Rutherford. You do need to know about their experiments, how they came about their discoveries, and I will go into them now. Thomson discovered the electron by using the cathode ray tube. The electron was the very first subatomic particle to be discovered, so Thomson is often credited with the one with proving that Dalton's theory was wrong about atoms being indivisible. He basically discovered that the electron is a negatively charged particle that is in all types of matter. He did that by using the cathode ray tube. If you notice, the cathode ray tube is called such because a beam is shooting from the cathode towards the anode. What Thomson did was nothing more than take a positive and negative plate magnet and put it on either side of the tube to see what happened. And he noticed that every time the beam would bend towards the positive plate. Well, opposites attract, so Thomson knew that the beam was made of negatively charged particles, which he called the electron. The picture on the left is a cartoon image. The picture on the right is a science teacher showing his students an actual cathode ray tube. If you notice, the beam is actually pointed away from the magnet. So what do you know about the magnet? It was the negative plate. Now, Ernest Rutherford and his gold foil experiment is an important one to know. Rutherford's experiment resulted in discovering the nucleus. He used alpha rays, which are positively charged particles, and shot a piece of gold foil with these rays. Now, the piece of gold foil was very thin, and he expected all of the rays to go straight through the gold foil because at this time they pretty much only knew about the electron. Most of the rays went through, but a few, 1 in every 8,000, scattered at large angles and even came backwards. Rutherford concluded that there was something really hard in the middle of the atom that was causing these alpha rays to bounce back, and he called this the nucleus. The fact that only 1 in every 8,000 came back proved to Rutherford that most of the atom is actually empty space. Think about that, your empty space. This is a picture of his experiment. Like I said, he used alpha rays. He shot them at the gold foil. He expected them to go straight through. Some of them deflected, which was kind of concerning, but the ones that got him were the ones that came straight back. And if you notice, that tells him that the center of the nucleus has all of the mass. It's very dense. It's small because you don't hit it often, but it's got a lot of mass. Mass over volume, lots of mass, little volume, high density. This is a picture showing what he expected to happen. So this is what Rutherford expected, go straight through, barely nick those electrons, and what actually happened. And if you see here, when he hits the nucleus dead on, that's when they're coming back. You need to be able to count protons, neutrons, and electrons. I know all of you know how to do this, but I'm afraid the summer may have fried your brain and you forgot. So the first thing we need to go over is atomic number, which is represented by the capital letter Z. Atomic number represents the number of protons in the nucleus of the atom. It also identifies what element the atom is. So when you look on the periodic table, which you all should have your own, the number at the top is the atomic number. That's the number of protons, and it also tells you that if it has 2 protons, that atom is an atom of helium, for example. Mass number is represented by the capital letter A. It represents the total number of protons and neutrons in the atom's nucleus. It has to be a whole number. You can't have part of a proton or part of a neutron. And notice, it does not appear on the periodic table. Students often have this wrong. Mass number is not on the table. So when I'm asking you to find the number of protons, neutrons, and electrons, here's how you do it. Protons are the atomic number. Neutrons are found when you subtract the atomic number and the mass number. Electrons are the same as the protons as long as the atom is neutral. If it's not, then you have to adjust the number of electrons, not protons, because protons are what makes it what it is. They don't lose protons. According to the charge on the atom. If the atom is positively charged, you need to subtract electrons, and if it's negatively charged, you need to add electrons. You need to know how to write a complete symbol, which we're going to practice soon. A complete symbol can be confusing for students because instead of the atomic number being on the top, like it is on the periodic table, it's actually on the bottom. Atomic number goes on the bottom, mass number goes on the top, both on the left-hand side, and then if there's a charge, it goes on the upper right. An ion is the term for any atom that has lost or gained an electron and is now charged. So in this case, this is a sodium ion because it has a charge of 1+. Alright, you need a periodic table to complete this. If you do not have one, I suggest you pause and get one up on your computer now so you can follow along. First off, the name of Al is aluminum. Look at the periodic table. The upper left number is the mass number. Right now we know the mass number is 19. The number that goes in the lower left is missing, the atomic number, but we can find that by looking at the periodic table. The atomic number of aluminum is 13. 13 means there are 13 protons. The neutrons is going to be the mass number minus the atomic number. So 19 minus 13 means I only have 6 neutrons. The electrons are the same as the protons as long as there is not a charge, and there is one. If it's 3+, that means you lost 3 electrons and you're down to 10. Now, I'm just going to erase this so I have a little bit of space. Okay? Now, iron, the symbol for iron is Fe. If you look at the periodic table, iron is element number 26. If it's element number 26, that means it has 26 protons. The neutrons were given to you, which means that the mass number is 56. And if there is no charge and there were no electrons given, we assume that it's a neutral atom, so there are also 26 electrons. Next one, scandium. Scandium happens to be element number 21 on the periodic table. That means there are 21 protons. Right away, I noticed that the protons and electrons are not equal. I've actually lost 2 electrons, which means my charge is a 2+. The last number I need is the mass number. In order to get the mass number, I need the neutrons, which isn't given. In this case only, take the number at the bottom of the periodic table, which is not the mass number, and round it. And the reason you can round it is because that will represent the most common isotope of scandium, which we will go over in a little bit. And so it's okay to round it because that's the most popular form of scandium there is. And in this case, scandium rounds to 45, which means there would be 45 minus 21, there are 24 neutrons. Lastly, silver. They gave me no information for silver, so I'm fully relying on the periodic table. The symbol is Ag. It's element number 47. And if I round the atomic mass to become a mass number, it's 108. That means I have 47 protons. Subtract those 2 numbers and I have 61 neutrons, and I also have 47 electrons since it's neutral. Isotopes. Isotopes are atoms whose nuclei have the same number of protons but different numbers of neutrons. That means they have the same atomic number but different mass numbers. For example, carbon-12, carbon-14, and carbon-13 are all isotopes of carbon. When listed like that, carbon-12, carbon-14, that's called isotope notation. Isotope notation lists the name of the element and its mass number. So in that case, the mass numbers are 12, 14, and 13. Mass spectrometry, which is something you may or may not have learned last year, I know my students did not, is very important in AP Chem. Mass spectrometry was the most convincing evidence that proved that isotopes even existed. What happens is that a gas sample enters a vacuum chamber, which just means there's nothing in the way of anything flowing, and when the gas enters, it's bombarded with a bunch of electrons. When it's bombarded with electrons, it becomes positively charged. It passes through a negative grid and some poles of a magnet to accelerate it, and it starts falling down the chamber. So at this point, all you have are positive ions headed down a chamber, okay, towards a detector. Now, as they accelerate towards the detector, they're not all the same mass because in a sample you may have different isotopes of, let's say, carbon or neon or whatever it is that you've injected. Now, this is designed as a bent tube on purpose. As soon as the ions hit that bend, they're not all the same mass to charge ratio. So when they bend, they don't bend the same way, and then they start to separate. When they separate, they will hit the detector in 3 different locations in the picture, but in reality it could be many points of contact. But in the picture you see 3 striking points on the detector. The detector then computes how many times it's being struck in each location and spits out what we call a mass spectrum. The mass spectrum shows you how many of each type of ion there was when it hit the detector. Important to note, if an element is also a molecule, meaning if it's like a diatomic, okay, the peaks will also be seen for the molecules as well as the individual atoms on the screen. Here's some evidence for isotopes. This is an example of a mass spectrum. This would be the mass spectrum from neon. And if you notice, everywhere you see a little peak, here obviously, a little one here, and here means that's the different masses of its isotope. Now, clearly, this one is the most popular. That's the one that's most abundant. 21 is very barely abundant, and then 22 is slightly abundant. So the height of the peak tells you how many atoms are present in that given sample. So here's some questions you guys could see on the AP exam. What type of analytical technique would give a spectrum like that shown? Your answer would be mass spectrometry. State why the spectrum of chlorine consists of more than 2 peaks. Okay? Now, it tells you here, peak 1 is due to the chlorine 35 ion. Okay? So if this is the chlorine 35 ion, this must be, if 2 bars over, that must be chlorine 37 ion. So what would it be at peak 3? Okay, at peak 3 you have a mass of 70. So you got to think, what could cause me to have a mass of 70? Well, if I had 2 chlorine 35s bonded together diatomically, I would get a mass of 70. The answer to the question of state why the spectrum of chlorine consists of more than 2 peaks is the presence of isotopes and diatomic molecules. Suggest what peaks 2 and 4 might be due to. Well, we already talked about peak 2. Peak 2 was the chlorine 37 ion. Peak 4 seems to be appearing at a mass of 72. At a mass of 72, what could equal 72 could be the chlorine 35 and the chlorine 37 ions combined into a diatomic molecule. That would be your 2 answers. Peak 2 is the chlorine 37 ion. Peak 4 is the chlorine 35-37 diatomic molecule. Here's another question. The diagram shows the path of a 25 magnesium plus ion through a mass spectrometer. On the diagram, sketch the path that a 26 magnesium plus ion would make and label it P. So the one we need to draw the path of is this one. This one is heavier than the 25 magnesium one. Will a heavier ion, as it comes through this chamber, will it bend more or less? And the answer is a magnesium 1 will bend less. So it's going to come out and hit the detector somewhere over there. Last topic is atomic mass. How do you report, this was a conundrum for scientists, how do you report the mass of an element if every single one of its isotopes has a different mass? Well, they came up with something such as a weighted average. A weighted average is not your typical average. It takes into account how abundant each of the isotopes are by multiplying its abundance by the mass number of the isotope. And it adds each of those together for every type of isotope to come up with the atomic mass. How are you going to get fractional abundance? Well, you could use the results from a mass spectrometer that tells you how often each one of those isotopes is appearing, or you can convert the given percent abundance back to a decimal, and that can be your fractional abundance. So those are your two options. When you calculate atomic mass, it should always make sense. So when you get a problem like this, 75.771% of the world's chlorine is chlorine-35, and 24.229% of the world's chlorine is chlorine-37. Take the percentages, which in this case you were given, convert them to decimals. Move it 2 to the left, and this is what I get. Move it 2 to the left, and this is what I get. Multiply them times their mass numbers, add them up, and I get 35.5 AMU. Now, my answer, I had two masses. I had chlorine-35 and chlorine-37. My answer is clearly closer to 35. And notice, that makes sense. More of the world's chlorine is chlorine-35 than it is chlorine-37. That's why when you don't have a mass number, you round the atomic mass on the periodic table, because the atomic mass on the periodic table is most influenced by the most popular or abundant isotope out there. So like I was saying, atomic mass is on the bottom of the periodic table. It is the number that you find right here. It's almost never a whole number. The ones that are whole numbers were not naturally found. They were man-made. The ones that you find, all other ones that you find in nature, have decimals because they're averages. Okay? You're going to know which one's more abundant by looking at the mass number, or by looking at the atomic mass and rounding it. So helium-4 must be the most popular isotope of helium because it's closest to the atomic mass. Last two questions. The mass spectrum of a sample of chromium shows 4 peaks. Use the data below to calculate the relative atomic mass of chromium in the sample. Give your answer to 2 decimal places. First, convert the percent to a decimal. 0.043 times the mass, 50, plus 0.838 times 52, plus 0.095 times 53, plus 0.024 times 54. Add them up. It says use 2 decimals. Final answer is 52.06 AMU. Ask yourself, does this make sense? Yeah, duh. 83.8% of the world's chromium is chromium-52, and my answer should be close to 52. Last question. If you had gotten a mass spectrum of this sample, what would it look like? What they're asking you to do is to draw one of the graphs like you would see coming out of a mass spectrometer. Make sure you label the axes. This side is relative abundance anytime you get a mass spectrum. And this axis, the x-axis, is the mass over charge ratio. Now, you have 50, 52, 53, and 54 as your masses. So let's make this 50, 51, 52, 53, 54. Okay? Now we're going to draw our graphs. Let me change colors so there's no confusion. And what you're going to do is you're going to draw the peaks. And remember, your peaks have to be indicative of how abundant your sample was as that isotope. So the first one, 50, is only 4.3%. So let's do this. 52, skip 51, is 83.8% abundant. Sorry, hard to draw straight. 53 is 9.5, so it should be about double your first peak. And maybe this one should be a little taller then. And then the last one is only 2.4%, about half your first peak. That is what your mass spectrum would look like had you put this sample through a mass spectrometer. All right, finish up, and I will see you in lesson 3.